Okay.
Yeah.
Crossfire, yeah, crossfire. Everybody knows crossfire. Half-Life.
I don't
know.
It's not Counter-Strike.
I don't know Korean game.
Look, Sean, they're just not cool, okay? Let's continue. Half-Life.
Oh, okay.
Yeah. You got that? Yep. So, there's not too much to do. This actually is a pretty easy lesson. It just continues from the equation we did earlier today, the one that you missed. So, we know that n equals n0 e minus lambda t. We did that earlier today. And we also know from maths class what this graph looks like. Exponential, yeah. It's exponentially decreasing. You know, something like this. We all know this from maths class. What is interesting about these graphs is that the time required for half to decay is the same, regardless of when we look at the sample. Let me explain this with some data, okay? So, here I have 100 moles. How long until I have 50 moles?
2 seconds.
2 seconds. Yeah? Okay, let's say I have 50 moles. How long until I have 25 moles?
4 seconds.
Yeah, so 2 more seconds pass. And it doesn't matter where I start. So for example, if I start at 12.5, how long until I have 6.25? 2 seconds. Yeah. So my point is, for these graphs, the time to half is a constant. No matter where you start, you have to wait the same time to get half of where you start. That's the key property of these graphs. So this gives us our definition, which is called half-life. And what we mean by half-life, well, maybe somebody wants to try and give me the definition.
Half-life.
Thank you, Monica. Yeah, go on. Yeah, it doesn't have to be the mass now. It could be the time required for the activity to halve, or the time required for the number of atoms to halve. So, the half-life of a sample is defined as the time required for exactly half the sample to become non-radioactive or stable. In other words, for half the radioactive material to be lost.
To become non-radioactive.
Yeah.
They're just lost, right? They're still radioactive, or far better gamma.
Yeah, it's just half of it is gone.
Okay.
Yeah. Got that? Yeah? No?
So is that infinity?
No, go on. Yeah, what do you mean?
Like, if it is 0, is there 0 divided?
Oh,
In real life, yes. Right?
what exactly is the question you're asking?
Like, can this process
Yeah.
reach the
because
end?
Reach to the end, or is it infinity, like half-life?
Our calculations imagine it's infinite, but in real life it's not infinite, because if you think about it, when there's only one atom left, you can't have half an atom. So once you're at the last atom, and then that decays, then there's no atoms left. Do you know what I mean? So it keeps halving, but at one point you have only one atom left, and you can't half anymore, so the process stops. You know, when you have 100 atoms, you can have 50. When you have 50 atoms, you can have 25. When you have 25 atoms, you can have 12 or 13. If you have 12, you can have 6, 6 you can have 3, 3 you can have 1 or 2, 2 you can have 1, but then after 1, the process must end. Yeah.
Oh.
Yeah. So it doesn't continue infinitely. Yeah? Got that?
Mm-hmm.
So, what I want to do now is I want you to Using the formula you got from the last class, n equals n0, e power minus lambda t, I want you to use that formula to get a formula for the half-life. That is, find a formula for the time it takes to lose half the n. See what you can find.
I think I put that in chemistry.
Yeah, this comes up in chemistry too.
Done.
What did you get?
1/2 n equal to NOE.
No, this isn't it.
N equal to 2n.
No.
Log 2.
Now, firstly, you're looking for t.
Log 2.
Oh, we are looking for t.
Yeah, that's what the half-life is, the time.
Oh.
A equal A0
You can simplify that.
E minus K 1 over 2.
You can simplify it.
Wait, teacher.
I'm not going anywhere, Lee. This looks like I'm about to fly out the window. I don't want a decimal. KJ? Okay. Andrew, you're lost. You don't know what's going on. You need to watch my YouTube video.
Yeah,
watch it.
Did you really? Did you like it?
Yeah.
Did you? Because I didn't get any notifications about likes.
Actually, I haven't watched it. Monica taught me.
Oh, now the truth comes out. Yeah.
Done.
Yeah. What did you get?
What you say?
Log 1 over 2 over lambda.
That's what she just said, and I told her you can simplify that more. Alright, let's have a look.
Why you?
Wait, give me a second. What is log 1
Go
over
on.
2? No, stop.
2 to minus 1.
No.
Minus 1.
E minus 1 over 2.
Minus 1 log 2 minus 1. Log 2 over lambda.
Is that E inside, teacher?
That's it.
Oh my god.
Oh, it has finished.
She got it. So, we want the time for half. So that means we want to have a half n0 here,
Yeah.
which I think you all figured out. We can cancel n0. We can log, and then we can divide by
100.
minus lambda. So we have t is log a half over minus lambda, which is log 1 minus log 2 over minus lambda, using the second rules of log, which is minus log 2 over minus lambda, which is log 2 over lambda, and in some physics books and formula books they actually write that as a decimal, 0.69 over lambda. This is the formula for the half-life. Which I'll write as t a half.
Teacher, why we can't change n to half n0?
Huh?
Huh?
That's what I want. I want the time for half the n0.
Initial and
Yeah? Yep, continue. Okay. So, this is the you can write the formula like this: lambda times the half-life equals log 2. I think in the formula book they write it as half-life is 0.69 over lambda. I'm not sure. Anyway, we have the result. So, let's have a look at an example. This is a very famous isotope, C14, carbon 14. Does anybody know why this is a famous isotope?
Yeah.
I don't know.
No, that's Sean.
Dinosaur.
You are not Sean.
Oh!
Lee, if you continue speaking, go on, Sean. Yeah, but why is it important?
Use C14 to detect
Yes.
another.
Give him a chance.
You need paper.
I don't know. I forget that word.
Okay, go on, Lee.
To calculate H. Oh.
Okay.
Right!
Yeah. You can use C14 to date, to measure how old something is.
Yeah, dinosaur.
Dinosaurs in particular. So C14 is carbon 14. Huh?
No, I mean the
Skeleton.
Archaeology. Archaeology, yeah. Yeah. Right. So the first thing, we'll do all this together. I'll let you try it first. Easy peasy. What is the half-life in seconds? Now, the half-life for carbon 14 is huge. It will take nearly 6,000 years for it to decay by half. So a huge half-life. So if I have 10 grams of carbon 14, then in 6,000 years I will have 5 grams. Whoopsie. So can you convert the time into seconds, please?
And during these 5,730,
Yes.
does it decay in the same speed or?
It does, because what happens is everything that's living has carbon 14 in it, a certain amount of carbon 14, and this is constantly topped up through the process of living. So what I mean by that is carbon 14 is in the atmosphere that gets absorbed by the plants. This radioactive material is also absorbed by the things which eat the plants. So even if you eat a cow or you eat a plant, you're eating something that has carbon 14 in it. Because even if you say don't eat plants, even if you only eat cows, no vegetables.
1, 8, 1, 10, 11. What? No?
I'm speaking.
Oh, really?
Yeah.
Sorry.
Even if you only eat meat, that meat ate plants. So it got the carbon 14 in it. Because you can't actually digest carbon 14, it's radioactive.
Why not?
So if a plant gets carbon 14 from the air, then the cow that eats the plant gets carbon 14 in it, and you have a hamburger and you get it in you as well. And this is at a constant level. When you die, you stop eating. Fact. Fun fact. When you're dead, no more eating. So it means that the carbon 14 that's in your body is not being replenished, so it begins to decay as normal. And when you think about it, most things are made from something that was alive. So if you find an old book in the ground, how can you know how old this book is? Well, the book is made from trees. So you can know when the tree was killed to make the paper.
What about steel?
Huh?
Steel.
You can't use carbon 14 to date things which are inorganic. So you can't use carbon 14 to date metals or rocks or things like this. But usually we use carbon 14 to date things that were alive and human settlements. You know, if there was a human settlement, sometimes they might leave some remains behind buried in the ground, like a fish or whatever they ate. So you could actually date the fish and then know how long the settlement was there. Okay, so do we have the time? What's it? 5730 times 365 times 3600.
No. 24.
Oh, times 24, of course. Right, so
24.
No, my days are 25.
Okay.
Right, this is how many seconds? Yeah. No, we shouldn't. We don't need 365.25. Is that what you're going to ask me?
Well, I mean half-life.
Huh? I'm only asking you for the half-life, yeah. And this is the half-life. Yeah. Right, what is the decay constant? So how do we get the decay constant? Log 2 over this. Yeah?
Yeah.
So I don't want to lose this. Shift store A. Okay. Log 2 over A. That's my decay constant in hertz per second. Okay.
Oh.
It's my lambda I got. No, it's my half-life. Yeah?
Teacher.
Is this a good question?
Yes, it is.
Okay, go on then.
Now
you're thinking.
So during these 5,730 years, right?
Yes.
There's leap years too.
KJ, I thought you were about to ask me about leap years, and I told you no, not 365.25, and I was mistaken, you weren't going to ask me that, but your friend to your left has just asked me what I thought you were going to ask me. So, teachers can sense questions about to arrive. I thought I was sensing your question. I was actually sensing this guy's question. No, we don't consider the leap years, even though there are leap years. We don't do this in the exam.
Okay.
Yes.
Why we not use carbon itself?
Oh.
I thought you were going to ask me this question. Yeah. Carbon 12. Carbon 12 is not radioactive. It's stable.
Oh.
So it doesn't decay.
Okay.
Yeah. We like carbon 14 because it decays. So we can use that to measure the age.
Okay.
Yeah.
How do you measure?
You would have to take a sample. And you would have to measure the carbon 14 per gram of the organic material. And this carbon 14 per gram is a constant if the material is alive. But the moment it dies, this decays. So you get less carbon 14 per gram.
How it decays?
It's always trying to decay. But while it's alive, it's constantly topping up its carbon 14 as it eats plants and animals that have taken the carbon 14 from the atmosphere. The source of the carbon 14 is the upper atmosphere. The carbon 14 is produced in the upper levels of the atmosphere, and it's the plants that take in this radioactive carbon. The carbon 14 is actually produced, I think it's when a neutron... What's the... I can't remember, but there's a collision that happens between neutrons and nitrogen in the atmosphere, in the upper atmosphere, when the energy levels are high, because of the gamma radiation from space, you can cause carbon 14 to be made, and this is soaked by the plant. What is interesting is the amount of carbon 14 per living material. We imagine that it's constant, but it could have changed. Like perhaps in the past there was more carbon 14 in the atmosphere, and so the plants had more carbon 14 in it, which means we could be misdating, because we are assuming the carbon 14 levels are constant and they only decay when it dies. But we have no way of knowing what the carbon 14 was in the past, and we have no reason to think it's changed, because we don't think the atmosphere has changed or the radiation from space has changed, so probably constant.
Teacher.
Yeah.
Usually we take in carbon 14 when we are living.
Yes.
But people live with different duration, so they have different carbon 14 in their bodies. How do we know this?
Yeah, it reaches, I'm not sure how, but it's like this. Let's say you eat 1 kilogram of beef. And let's say there's 1 carbon 14 in 1 kilogram of beef. What your body does, as you know, when it needs to rebuild your tissue, it takes the protein from the beef. So your 1 kilogram of beef will become 1 kilogram of you, minus the waste that comes out. So it's the concentration that matters. If the beef had 1 gram of radioactive material per kilogram, then it means when your body uses that to make you, it will have the same proportion. So you're thinking like it's like a toxic, that it gets into your stomach and it builds up, and the more you eat, the more it builds up. But rather it's like everything is tainted with this, and when your body builds itself from its materials, it has the same concentration. Because your body doesn't really have any way of getting rid of the carbon 14, it's radioactive material. So it'll be constant, it'll be the same proportion for every living thing. Yeah? Yes?
But still, if we know the proportion, we need to know the mass, right?
Yeah, so we look at it on a per gram. So we say, what is the carbon 14 per gram? So let's just imagine it's 1 microgram per gram. when you're alive. That would be true for everything per gram. So you do it on a per gram level. Not like how much in total, just how much of a gram of that specimen. Yeah? Sean?
Where are the carbon-14 goals are?
I don't know what it decays into. It might decay into
Physics.
carbon and nitrogen. I'm not sure. I'll look it up. But it decays. It might become carbon or nitrogen. What's the proton number for nitrogen? 7. 1 more than carbon. Oh, carbon 6.
Carbon is
6 protons.
yeah.
Yeah, and nitrogen 7 protons?
9,
Yes,
8.
Yeah, because it has 5 valence electrons.
Anyways, it might become nitrogen or might become stable carbon. I'm not sure. I'll have to check it. Okay, next. The molar mass of carbon-14 is 14 grams. How many moles are in 100 grams?
100 divided by
Huh? This one here? What's wrong? Yeah. Oh, I actually say it. Oh, there you go, Sean. Carbon-14 decays into nitrogen-14. Yeah.
That means it's chemical reaction.
No. The alpha, beta, gamma decay changes it. Okay, how many moles do we have? We have 7.14 moles. Okay? Carbon-14 will decay into nitrogen-14. In 100 grams of carbon-14, how long until we only have 25 grams of carbon-14?
2 times.
2 half-lives.
Yeah.
First goes 100 to 50 and 50 to 25. So the answer will be 5730 times 2. 11,000 years.
Yes.
Yep.
Yes.
And finally, how long until less than 1 gram remains? Now, did I ask you an exact amount?
No.
No, I said how long until less than 1 gram. So I can ask you to estimate here. Okay, so think about this. We start with 100 grams. After 1 half-life, we have 50. After 2 half, 25.
12.5.
Yeah.
6.25.
Yeah.
3.125.
125.
1.5.
Go.
0.7.
1.5. So 7. 7 half-lives.
Wow.
40,000 years. Yes. So this is why it's useful for dating. I don't know how small you can detect it. I don't know what's the threshold. I think you can use carbon dating to maybe date at this level 40, 50,000 years. But after that, the carbon-14 amounts get so small it's hard to detect it in the sample. Yeah. And of course you can see if you're trying to date something which is millions of years old, the carbon-14 will not work. So you can't actually use carbon-14 to date dinosaurs, I'm afraid. They're too old.
So what they use for
There are other types of decay that has a longer half-life. And they use other methods too, like the level it was buried in the earth. So, yeah.
That's not very accurate.
No, it's not. It's not. But if the dinosaur is dead 10 million years or 10.1 million years, who really cares? You know?
No, I'm not talking about that accurate. Like some people say, like.
Oh, it's even yeah.
Like some researchers think this rock is like 10 years old, and some researchers think this rock is like million years old, like that.
It has a half-life as well that you can date. The rocks are difficult to date. You would have to more understand the geology. Yeah, some people don't like carbon-14 because it makes it look like the Earth is older than it is. But these people are, how can I put this politely?
Joke.
You don't have
No.
to be politely based recording.
Well, they're scientifically ignorant. They have a belief that the Earth is less than 10,000 years old. So any sort of science evidence which says the Earth is more than 10,000 years old is something they don't accept. Uranium, yeah. Yes. There's many different techniques that you could use to date different parts of the Earth. You know, like the coral reef in Australia, that grows at a certain rate, so you can know how long old that is by how much there is. You know, in the caves, when you see the stalagmites forming, you can date the caves by how long those stalagmites are. There's different things for different situations. For anything that was once alive, the carbon-14 is a good way to date it. Yeah. Okay, so 40,000 years. Right. Okay, so that's it then. We can try this question. There's only the one question. It's quite easy. You should get that question finished now, and once you have that question finished, you can go.
I saw one
Like never.
engineering student go to geology.
Say again?
I saw last year one engineering student go to geology major from the IFC.
I can't remember who that is now.
I don't know that last year or last year, but anyway, this last month I think.
Yeah. Oh yeah, carbon-14 dating would be studied in geology. Yeah.
I was curious like how engineering student goes to the geology
Because
part.
this is offline.
Well, imagine the student wanted to study geology. Would they pick business, science, or engineering? Which would be...
So we go.
But then they'd have to study biology.
Geology is related to biology.
No, I'd say geology is closer to chemistry and physics than it is closer to biology.
Oh, it's
Yeah, because it's a material science. You know, how do plates and mountains move? How do rocks form? You know, it's more closer to materials like physics and chemistry than it is biology.
But like people don't think geology as much as like there's science as well. But
No, I wouldn't say that. The only problem with geology is that it doesn't have many applications. It's not like physics and chemistry where you can build things. So this is why it's not emphasized as a science. Just because you study geology to understand the past, not to make a new computer. So this limits its interest. You know.
Any amount.
Can I close this now?
You become 100.
I have an engineering question.
Let me just stop this.